Hey folks, Todd Coburn here, the Aerospace Structures series. This lecture is on micromechanics. So we've been looking at the lamina itself, looking at the stiffness and the strength. Now we're going to, instead of developing those properties from other sources like testing, we're going to look at how we can estimate those properties from the constituent properties. Let's see how it works. So this is a little look at a typical fiber reinforced lamina. We have the lamina itself, as you see on the right, and then we have a matrix material and a fiber material. We're now going to look at how we can build this up by looking at the properties of each of those constituents. So we are going to return to our two concepts of macromechanics and micromechanics that we've discussed already. Remember, macromechanics means we've looked at the lamina and we've figured out the properties of how it behaves as a whole. We don't actually need to care at that level what the constituents do or contribute, as long as we have a solid estimate for what the stiffness is and the strength is at the lamina level. That's the macromechanics method. Micromechanics, the way we're going to use that term, is looking at those constituent parts, what are their properties, and how can we estimate the stiffness and strength for the lamina. That's what we're going to do. So, quick quiz. Which approach tests the lamina to determine properties? Micromechanics or macromechanics? That's right, macromechanics. Okay, how about which approach estimates properties for the lamina from the properties of its constituents? You got it, micromechanics. Okay, so let's take a look at this lamina again. We got a couple different approaches we can apply. One is a mechanics of materials approach, and another one's an elasticity approach. The mechanics of materials approach is going to use the things we learned from mechanics of materials to estimate the properties. Elasticity is going to delve into the principles and methods of elasticity to develop that. It's going to be harder. We're going to stick with the mechanics of materials approach. We actually have potential to gain a little more accuracy using the elasticity approach, but all these analytical models are going to tend to fall short without a little bit of testing backing them up. So our objective is to estimate the stiffness and the strength. Remember, this was the stress-strain relationship for an orthotropic material on a stiffness matrix basis and on a compliance basis. And now we're going to need to figure out what all these constants are. And we can suspect from what we've seen from other materials, it probably has to do with the E's in the various directions, the G's and the Poissons ratio, at least from a stiffness point of view. We could write it like this mathematically, saying that each of these constants are a function of all these other little variables, where V sub F is the fiber volume fraction. Okay? We can do this on a stiffness basis, and we can also develop the strengths as well. This is using actually Jones nomenclature, which uses a capital X and Y for the constituent allowables, and what we did is using a capital F, but we're going to talk about that next lecture anyways. Okay, so I'm going to rely on some of the figures from Jones to develop this idea. So our lamina we're going to use a bunch of assumptions as we do in typical engineering fashion. First of all, when we look at the lamina, we're going to say it's initially stress-free. It's not always 100% true, but we can kind of approximate it, assume that's true. We're going to assume it behaves linear elastically. That means even if there's yielding, we're going to pretend there ain't. We're going to say that it's homogeneous at the macroscopic level and that it's orthotropic at that level. Okay? When we look at the fibers, we're also going to say that those are homogeneous, they're linear elastic, isotropic, regularly spaced, perfectly aligned, perfectly bonded. And for the matrix, we're going to say that that's homogeneous, linearly elastic, isotropic, and void-free. These assumptions will allow us to build up a method that works, and with some error, but reasonable because of the way testing has validated this. But we'll kind of take a look a little bit about that as well. So we have our fiber and matrix, which make our composite lamina. And if we look down on the lamina, we're going to be doing this throughout this lecture. This is a sketch from Jones. We're looking down. We can see the fibers. We can see the matrix. Once again, as we've said in my book and elsewhere and here in Jones, we're going to kind of look at this little model as if the fibers are distinguishable from the matrix. Remember, if they're properly wetted, it's all going to be one mass, and you're not going to be able to distinguish very well the fibers from the matrix unless you use a microscope. But for the purposes of building up our approach, we can use this model. What this looks like is we have a bunch of fiber and a bunch of matrix as distinguishable volumes. It's not really true, because the matrix should be completely wetting the fiber such that everything is in perfect contact and bonded together with that. So any cross section, you can't really distinguish those constituents very well from each other. All right, so we're looking at the unidirectional lamina, and what we're going to do is look at a little representative element like this. If we pull out one little element, it has a little bit of fiber and a little bit of matrix. And we're going to look at the smallest element. That's going to be our little volume element, the smallest element that we can just say it's the same. Remember, it's kind of like when you're doing cut and paste on the computer, you grab one little piece and you splice it all over the place, kind of like that. What's the smallest little element we can make that has the appropriate ratios of fiber and matrix, and such that we can just move that anywhere and it's still valid. If we have a woven fabric, that's a little trickier, because now the weave pattern itself will influence properties in the two directions. The fact that the fibers are not perfectly straight, that they're leaping over each other, is going to change stiffness and strength and stability. But we're going to typically ignore those ideas, except for the variances we're going to use from testing, and just grab the smallest element that looks like it's roughly representing that weave. Okay? And what we're looking for here is we're looking for determining those properties. So we can say, all right, with this little sketch, this little graph from Jones, we've got all of our properties are going to be a function of our fiber volume fraction. Because, right, it's a function of our fiber, it's a function of our matrix, and the volume fraction says what percentage of that entire element is fiber. So we can look at the matrix or the fiber volume ratio, but by looking at one of those volume fractions, we can actually understand what's going on everywhere. So we're going to do it as a function of the fiber volume fraction, V sub F. We're going to go from 0, that lamina can have no fiber, or it can be 100% fiber from 0 to 1. And we're going to look at if we have no fiber, we're going to expect to see the matrix value. If we have no matrix, we're going to expect to see the fiber value. And in between, it can be a linear relationship, it can be a straight line, it can be a curve, parabolic, who knows, you name it. And we would have to determine that either with analysis or testing. All right, so our first little element, let's go ahead and look at E1. Let's try and develop the modulus in the principal material lamina direction. This little sketch from Jones kind of shows our little representative element. Once again, we can see the fiber a lot more clearly than we actually would be able to, separated from the matrix, which wouldn't be that separate. And we're pulling on it in the one direction, and if we pull on it in the one direction, we're going to expect it to get longer. We're also, because of Poissons ratio, going to expect it to get narrower in the other direction. So we're going to see a displacement in the lengthwise in the pulling direction, and we're going to see a displacement in the transverse direction. That's the one direction and the two direction. Okay? based on that single stress in the one direction. If we take that length of our element and say that that length is L, and we have a width W that we'll deal with in a little bit, we're going to have to use some assumptions or simplifications. We're going to say that the fiber and the matrix have the same strain in the fiber direction. They have the same initial length, so if the displacement is applied uniformly to everything within that element, then the strain, the deflection over original length, will be the same. This is a little bit of a stretch, but it's close enough for government work. We're also going to say plane sections remain plane. Well, that kind of fits with our first assumption as well. Okay? So when we try to develop our model for Young's modulus, we're going to start by looking at the strain. If you think back, strain is just deflection over length. If we say the strain of the entire lamina in the principal material direction 1, we call it strain sub 1 is equal to the deflection of the whole element divided by the length of the whole element. That is the strain in that unit piece, that little representative element. Okay, that's old news. And we also know that from Hooke's law, we can write Hooke's law against the fiber, against the matrix, and against the lamina as a whole. If we write Hooke's law against the fiber, because we're pretending that that's homogeneous, therefore we've got the simple version of Hooke's law, which is stress equals EE. So the fiber stress is related to the strain through the modulus of the fiber. We could say the same thing for the matrix and the same thing, that was the fiber that we did, the matrix that we did, and then the element itself. Now remember, we're assuming that all these strain the same, so instead of seeing the strain in the F in the fiber and the strain in the matrix, we're calling that strain 1 for all three. The strain is the same, the only thing that's different would be the stresses and the moduli in that case. We know our force is just the stress times the area, so we can write that relationship. The total force is going to be whatever stress the fiber carries times its area, whatever stress the matrix carries times its area. We take this and drill this puppy down, and when we plug in our little for the stress, that EE from Hooke's law for each, we can write that this way. We can then rearrange that using 10th grade algebra, and we can write it like that. Recall that the fiber volume fraction is just the area of the fiber times the length of the fiber over the total volume of the element, which we can write as an area fraction, and the volume fraction, therefore, is written this way in a similar manner. If we plug those puppies in, we now get our equation for estimating E1 for the lamina from the E of the fiber and matrix as a function of the volume fraction. This is the apparent modulus, or the approximate modulus, of the composite lamina in the direction of the fibers. That's the principal material direction. And we call this method of developing it using a mechanics of materials approach the rule of mixtures, because it's saying, hey, the total property is a function proportional to the relative amounts of each, or mixture of each. Okay? All right, great. Sounds good so far. Let's go ahead and look a little further at this. This is what we developed on the last slide. We could think of this as a spring model where we've got multiple elements acting in parallel in a spring. This is the way it behaves. We see that modulus. The modulus, if we have no fiber, it's going to be the matrix value. If it's all fiber, it's going to be the fiber value. And in between, it's basically going to be a linear straight line. So folks say that this is a fiber-dominated property. If we plot some test data on that, this little plot is out of Jones, and it looks reasonable. Looks like we just slightly over-predict the modulus with this approach, but it's close enough for government work. So this is mostly accepted as being good enough for E1. A guy named Ekval comes along, and he proposes a tweak to that. he introduces another term. He switches out the E matrix with this new term, and with that we get this kind of, so far, if we had a lamina with a Poissons ratio of the matrix that was 0.2, you'd see that ekval doesn't really change anything. You can't even distinguish those two lines. If our Poissons ratio pops up to 0.5, it's still pretty good. So while ekval slightly tweaks it, it's not a big deal for E1. Now this equation from ekval is not in the Composite Strength Handbook or my Composite Strength Handbook. It's in Jones's text and some others. So if you are one of my students, you're going to want to write these equations. And you don't need the graphs, just the equations, so that you can use ekval's method. Okay. All right. Now looking in the widthwise direction, the 2 direction, remember we have our little representative element. We already pulled on the 1 direction. Now we're going to pull on the 2 direction. That's across, perpendicular from the fiber direction. Okay. In that direction, once again, our little element looks like we got a body of matrix, a body of fiber, a body of matrix. That's a gross simplification. We know that it's going to be all kind of mixed. It's going to be hard to see. You're not going to be able to take a section cut and get only matrix. You're going to get a combination of matrix and fiber. Regardless, that's our approach. We've got our 2 dimensions, the length dimension, which we're not going to need now, and the width direction, and we're going to now evaluate using that approach. Now our fiber and our matrix no longer picking up load together because we're pulling the other direction. So if we pull on it, the matrix, well, at least with this model, can pull away from the fiber. When we pull on it, the stress is going to have to go through the matrix, through the fiber, through the matrix, which means we have a cross-section of stress in each one. Not really true, but it's the approximation we're using. Okay, so we can develop our E2 using this approach. Our stress in the 2 direction is going to be equal to the stress on the matrix in the 2 direction, which is equal to the stress in the fiber, because that force is going through the matrix and then the fiber and then the matrix in our model, one at a time. Okay, we can write, now this is delta W is the change in width. Don't confuse that with the weight, right? Change in width, that's the deflection. And we know the deflection divided by the original length is just the strain. So the change in width divided by the original width is the strain in the 2 direction. So we can write the change in width is just the strain in the 2 direction times the original width. And that means we're going to have a deflection of the fiber, which is the strain of the fiber times the width of the fiber, and a strain in the matrix times the width of the matrix. And we can calculate what each of those are. The fiber width can be approximated from the volume fraction with this model, and the matrix width can be approximated from the matrix volume fraction, which is just 1 minus the fiber volume fraction, by the way. Plug these in and we can write our equation this way. And if we note that our Hooke's law says sigma for the strain in the 2 is just the stress over the modulus. And we can write the same thing for the fiber and the matrix. Plug all that in, we can write our equation this way, which we can now rearrange with 10th grade algebra into this form. This is our mechanics of materials expression for the apparent modulus. So now we have predicted the E1 using the constituent properties. We have estimated the E2. Okay, let's see how well this one works. Once again, to do that, we're going to jump back to Jones's text. He says that we're doing this since we're loading the matrix, then the fiber, then the matrix. This is like a springs in series. And our limitations are, we have, or another problem with this model is now, when we pull on it this way, when we pull on it, that's going to cause a transverse strain because of Poissons ratio, and we're going to get a different transverse strain than we do at the two elements at the boundary between the matrix and the fiber. We've got a mismatch, which is not really possible if they're actually bonded together. Also, our transverse stresses are not going to be identical. Regardless, we can look at how this performs. This little graph from Jones says, well, if you have, if the ratio of the fiber to the matrix, if the ratio, let's just think about different materials, and they have a different modulus ratio. Modulus of the fiber to modulus of the matrix. Jones here is plotting three different potential materials. One of them, the fiber and modulus, have the same stiffness, so the ratio is 1. That's this flat curve. It says no matter what your volume fraction, you have the matrix modulus, because the matrix modulus is the same as the fiber modulus. Okay, that's one extreme. Now, if we have a fiber that's 10 times stiffer than the matrix, you get this second curve. You'll notice by just going from a ratio of 1 to a ratio of 10, a factor of 10, we got a completely different response. We see down, if we have almost no fiber, we have something close to the matrix property, but even a little bit of fiber rapidly increases the stiffness closer to approach the fiber matrix, fiber property. And if we have, if we have a fiber ratio, if our fiber is 100 times stronger, we are going to see a similar trend, but not hugely more. So the biggest change is by having, if our fiber is like 10 times or more stiffer than the matrix, we're going to get a lot of benefit for having fiber in there. And you'll notice once we get up above the 60, 70-ish%, we start seeing some really good properties. Now the problem is, and my book doesn't really talk about this, I think Jones does a little more, but it kind of skirts over a little bit too. The problem is, if you don't have enough matrix, people might say, hey, we'll just go with like 95% or 100% fiber, but then you have nothing bonding it together and all you have is tension capability. If you don't have enough matrix, you won't have enough volume of that matrix, which actually bonds the fibers together, makes them act as one, and makes this thing act like a unit rather than a bunch of strings. It's critical to have enough matrix. You actually want as little matrix as possible while still having enough to completely bond those fibers. To fill between, remember the fibers consist of a bunch of filaments. That all has to be impregnated with our matrix as well as between the strands, and in order to get composite behavior, acting together as one. Okay? This is a little sketch of a correlation from Jones again. Here we see our matrix going to our modulus, how it changes for different volume fractions of a particular glass epoxy. And we see that the test data shows that we're under-predicting E2. E2 is higher than we're predicting, at least for this material, which makes sense because we actually have a lot more interlocking. We never can just load the matrix by itself. Regardless, for this reason, we tend to say that this is not as accurate of a method, although it is used a lot out in industry. So, once again, if we look at Ekval's improvement for E2, this is our rule of mixtures, and Ekval replaces the modulus of the matrix with this little term again, and this is how that plays out for Poissons ratios of 0.2 and 0.5. You'll see 0.2, it's not really a hill of beans of difference, but now at 0.5 you do see some noticeable difference. It's not very much, but it's noticeable. Once again, students of Aero 40360, make sure you write these into your handbook, and you can stick them on the bottom of this page would be an appropriate place. Also, those of you in industry, who may want to use this in the future can do that. All right, so let's look at Poissons ratio. We're going to focus on the 1-2 Poissons ratio, and recall that we can compute the 2-1 from the 1-2 when we need to using our equations we developed earlier. So Poissons ratio on the 1-2, remember Poissons ratio is defined, or the Poissons ratio 1-2 is defined as the negative of the strain in the 2 divided by the strain in the 1. So if we're pulling on this part in the one direction, the stress is in the one direction, then the strain in the transverse direction divided by the strain in the one direction, the direction we're pulling, the negative of that is actually defined as Poissons ratio. Remember, from this, we can estimate what is the strain in the transverse direction by just multiplying Poissons ratio by the strain 1, or the negative strain 1, okay? So our simplifying assumption here is our fiber strains are identical to our matrix strains in the fiber direction. Well, if our materials aren't, if our fibers, so imagine we're in the matrix, and if we're pulling on this and the fibers get pulled through, which means failing the matrix, or if they're a large enough diameter that they deform and strain differently, then this assumption is blown. But actually, this is a fair assumption for our purposes for this particular element. Our fiber strains are going to be identical to our matrix strains. Identical is a pretty strong word, but close enough for government work. Okay, so we can write our equation for the deflection in the widthwise direction, right? The deflection in the widthwise direction is just that divided by the total width is the strain in the 2, once again, like we saw before. We can write that equation this way. And if we plug in our relation now from up above, then we can write it this way. We can now recognize that part of that deflection occurs in the matrix and part of that deflection occurs in the fiber. No problem. Where once again, we can apply this principle to both representative deflections. We can stick these in and rewrite this and simplify using 10th grade algebra to get our rule of mixtures estimate for Poissons ratio 1-2. This is it. This is how it's graphed, going from one to the other with a nice linear line. And folks say that this is a neutral property. It's not necessarily more dominated by the fiber and not dominated more by the matrix. So we can now do the E1, the E2, and the Poissons ratio. Well, let's go ahead and look at our G12, our shear modulus, or our modulus of rigidity. Once again, we have our representative element. Once again, I'm borrowing the figures from Jones, who goes into this in a little more depth than I'm doing here. And we're looking at our element, and we've got it loaded in shear, and we can see our shear deformations, but now because we've got multiple members, multiple constituents, and we're pretending those all act separately instead of together, we can draw it this way, which says we got about half the strain in the matrix, half the strain in the matrix, and then the strain in the fiber. This obviously is a gross simplification to assume that these strains are the same. But we can go ahead and write our equation like this. Once again, we're going to apply Hooke's law for shear strain on our matrix, fiber, and total lamina. Okay, our deflection is simply total deflection in this direction, right? It's going to be the total lamina strain times the total width of the element, no problem. And the deflection is going to consist of deflections of the matrix and deflection of the fiber. No problem. Which we can write each of those this way. Once again, recalling our equation for strain, the deflection of the matrix is just the width times the volume fraction of the matrix times the, the deflection of the matrix is the width of the element times the volume fraction of the matrix times the strain of the matrix. And then we can write the fiber equation similarly, plug all these together, and we get our rule of mixtures estimate for our shear modulus. Okay, If we plotted that out, it looks something like this. This is showing if that ratio of G of the fiber to the matrix is 1, it would be a flat line. And once again, with even about a 10-fold increase in shear modulus, we're going to see a lot of benefit for adding fiber. Correlation for this to testing is similar to E2, which means it tends to be a little overly conservative. The stiffness is probably a little bit higher than what we predict with this. Okay? So that is how we can derive from a rule of mixtures approach using a mechanics of materials approach, and what we precisely call it is the rule of mixtures. We got E1 predicted, we got E2 predicted, and we got Poissons ratio and the shear modulus. All predicted with fairly simple methods, and it has reasonable correlation for the amount of effort we put into estimating it. It's a great first step in estimating the properties of a material. There are some other relations that we can utilize when we're doing calculations. Sometimes, remember, we have our volume fraction, which we can write as the volume, the actual volume of the fiber divided by the total volume of the element. We can write that for the matrix as the total volume of the matrix over the total volume of the lamina or composite. And the summation of those obviously has to be equal to 1. So we can write the matrix volume fraction as just 1 minus the fiber volume fraction. A lot of times we're going to find out, like in our appendix, we're going to know what the fiber volume fraction is. If we need the matrix volume fraction, we can just use this equation to compute it from the fiber volume. We sometimes will need the mass fraction, which we can write this way. And a density relationship can be written like this. For the lamina, we're using the subscript C for composite, but that's talking about the lamina. And here's a couple other handy relations that we might need. So all of these in your handbook. The only thing from all this, some of this derivation is not provided. I'm just providing the equations in your composite strength handbook. If you want the derivations, you're going to have to go to Jones or more detail on that, or other texts. And the other thing is Ekval's equations are not in my handbook currently, so you're going to want to write those in if you want access to those. Okay, another idea now is, remember, if we have thermal, if we have a temperature change on an element, we know for isotropic metals and things, we know that the strain is just alpha delta T, the coefficient of thermal expansion times that change in temperature. And we can estimate the deflection by just multiplying that by the original length or dimension to get how that is going to change any dimension. This was true for metals, and it's also true for composites. Now, in order to utilize this, we're going to need alpha, and so we can estimate the coefficient of thermal expansion for the lamina from the coefficient of thermal expansion of the constituents using a rule of mixtures approach. I'm not going to derive it. This is the equation we can use right here. The the coefficient of thermal expansion for the fiber times its modulus times its volume fraction plus the values for the matrix. All that divided by E1. And our coefficient of thermal expansion in the two direction can be computed this way. Okay? Now, one thing that we haven't probably dealt with metals, and that we do need to deal with composite structures, because a lot of times these will, especially the matrices, will absorb water, is moisture-induced strain and deflection. Actually, when we have something that does absorb moisture, we can approximate the behavior in the same manner we did for thermal loads. And we introduce the coefficient of moisture expansion. Beta is what we use there. Inches per inch per pound per pound. And the deflection then is just that strain times the original dimension. So if we experience a moisture, and we're going to use C for moisture concentration, lowercase c for the moisture concentration. So like 0.1, 0.2, 1% would be huge, that kind of thing. So if we get a moisture change, so let's say we have a rocket that's sitting out on the pad in Vandenberg. It's sitting out there with the sun cooking on it and the moisture coming in because of the humidity. That's going to develop, that moisture is going to diffuse into the material, and it's going to experience a change in dimension. It's going to experience strain and deflection due to that moisture change. All we need to do is know what the beta is, the coefficient of moisture expansion, multiply that by the concentration of moisture, and that will give us the strain, multiply that by the original dimension. That tells us what the deflection is for that. This is how we can estimate those. I'm not going to derive those either. Beta 1 in the one direction and in the two direction. Now the problem here is, you'll notice we got a lot of terms. That's a problem for some. We've got fiber values and we have matrix values. We have densities as well, and we've got moisture concentration. Now you'll notice with thermal properties, a lot of times we can neglect any change in the thermal properties based on the actual temperature. We just grab the value at room temperature, and it's often close enough for government work to use for other temperatures. Not so much so with moisture. Moisture is a function of the coefficient of moisture expansion is a function of the moisture content. So as the moisture content changes, those coefficients are changing. That makes it harder. However, if we look at this, many fibers will absorb no or near no moisture. They have very low coefficients of moisture expansion, sometimes 0. If that's true, then the beta F terms go away, and they can't take with them, when they go to 0, they take that moisture concentration term with them. Can cancel out of that equation. That simplifies our equations greatly, and now we can just get the matrix coefficient of moisture expansion and use that to estimate our one and our two direction moisture coefficients. Now we can actually simplify this further. If our modulus of our fiber is a lot bigger than our modulus of our matrix, then that ratio of moduli can be is negligible, and that will drag out that last term. These are our properties. Remember, for our constituents, our fiber and our matrix, we're going to go to our appendix to get the values for our class 4360. You can go to any good source of properties or do your own testing if you're out there in industry. So that is our micromechanics approach to developing the stiffnesses we're going to need for composite analysis, specifically for the lamina. Next time, we are going to look at how we can estimate the strength properties of the lamina from the constituents. So stay tuned.